welcome. So I wanted to take a minute here and go over what I think a 6-week unit might look like for teaching the T3 program. And I shared it with Chester on the plane back, and he said, you need to make sure to explain this to people what it means. So we've got it in written form, and I'll be working on tweaking this down to a more palatable level, but here's my explanation of what your week 1 through 6 would look like. Because the first thing to note is that this is not a programming class. This is, our goal is, as I wrote here, okay, we'll start again. So for week 1 to 6, I consider the week 1 getting started week. That's the week where and you're introducing this pie to your kids, and they're so excited. Very first lesson the first day is brush-bot growth mindset. They'll be learning about fixed versus growth, engineering design process, and the work of Carol Dweck. Remember, every one of these lessons are thought to be like about an hour-long design. The second day, a brush-bot competition. I do want them to take home their brush-bot after the first day so they can tweak on it and mess around with it at night. When they're done with the brush-bot, a learning style survey of some capacity that helps us figure out, where do you fit into learning technology, and maybe something about your skill level already with Minecraft and other things. The next day, really, we'll sell the project, a promo video, what kinds of cool things are you going to do with Raspberry Pis, and a little bit about the history of computers. And Raspberry Pi is really a modification on that history of computers. It's an effort to get back to basic computing. Lesson 4, box build with startup sequence. We're going to give you those computers where you have to build a portion of it. So it's not going to take super long time to build your box, but at least an hour. And then once you log in, turn on your Pi that first day, there's personalizing it, connecting it to the internet. There might be a little bit of backup work that had to happen in order to make sure that you could connect it up to the internet, but that's there. The 5th day is still your first week. You're networking with Minecraft. And this is big in terms of human and physical networking. There's a lesson there. Growth mindset, what does team building look like? And logging into your Pi over the network with VNC. Meaning that if you wanted to work on a big screen, but you plugged your Pi in, you could use a big screen and go through the network in order to do that. Again, there'll be a tutorial on that so you can understand. But this is where kids get into networking in Minecraft and start playing. The whole second week is about interacting with your computer and coding. When we think of this, it means we're going to teach them the programming language of Python just a little bit, using Python to code in Minecraft using the API. That's where we're playing Minecraft, and now we're starting to tweak it, and we're watching what happens. Think of a Minecraft like a graphical user interface, and Python is running behind it, and you're making changes to it. Kids will get good at this. During the second day, we'll use GitHub and get more code. We'll tweak Minecraft, get a screenshot program. On the third day, we'll allow some sort of competition to happen with Minecraft. And I find this is really fun, and kids get very excited. Even the high school kids who think they're too cool really enjoy trying to do something with a competition. I've got an example video of what that might look like later. Also this day we'll do a demonstration of the Sense Hat. Remember, I'm only sending one per the teacher kit, so unless all of your kids have a Sense Hat, just the teacher's Sense Hat can go into Minecraft and look over that world to kind of get an idea of what it looks like. If you listen in the background, I'm here at school, the kids are chanting as they start up class. So anyway, human computing activity the next day. So we'll learn a little bit about how is a computer interacting with the programming language. And I think Scratch is the first lesson we'll go through, using Scratch to program basic programming concepts. What is a loop? What is a a conditional variable, that kind of stuff. And yes, I will list that out in terms of step by step. What is a reaction time game, making an animation or possibly an internet meme. So by the end of that week, they will have played with Scratch as something that they think and program with, and they'll also have been introduced to Python. We're not going to spend much time the rest of this course in doing the details of Python because it's got a steep learning curve, and we want kids using stuff fast. But we will understand that it's out there, and we will understand that it does relate back to your stuff. In the third week, that's when the GPIO pins will come alive, and we'll think of a better way of selling this first unit. But hooking up a GPIO pin, lighting an LED button with Scratch, what are the basics of circuitry? I'm going to imagine having a hook, having a teacher saying, I really want a Scratch reaction game, something that will be like a quiz show where you push a button and I find out which of my students push the button faster. So we'll learn to make that kind of thing, make a GPIO button with Scratch, and level it up to hooking up those little alligator clips and make a whoopee cushion reaction game. Node-RED and GPIO pins will do the exact same thing that we had just done with Scratch, and now we'll do it with Node-RED and the GPIO pins. Make buttons, light an LED, see some videos that show why Node-RED is pretty powerful. My hope is to get them excited and let them see that it's an easy way of organizing code with the graphical user interface. There's something called a power tail. I can't remember what its official name is, but a power tail allows you to take the pins where you plugged in an LED bulb and plug it into a lamp. So you can turn a lamp on and off in the same fashion that you turn an LED bulb on and off. And we'll get them excited about that day. On lesson 4 of that week, we'll set up a camera, take pictures with Node-RED, import new code sequences or libraries, see how easy that was, setting up the camera LED ring. Using the last day, we'll use Node-RED to set up a sensor, a weather sensor, use a little servo, and play around with combining these tools in a sequence. Remember, this week we were all learning about getting the GPIO pins to make the programming that we were working on really come to fruition. In our 4th week, we're going to introduce students to 3D printing. This means that they have access to a computer that's powerful enough to use Tinkercad. As we mentioned there, Tinkercad is a web-based program. It's completely free, and there's some tutorials that we will be this week putting onto the website so that you can access and follow those things. On the first day, we'll just get to know Tinkercad. The second day, we'll learn how the 3D printer you have works, how to load filament, unload, how a slicer works, what supports and overhangs are all about. And then we'll take 2 more days to do more advanced stuff with Tinkercad. One of the lessons will include importing and editing existing files from somewhere like Thingiverse. So remember, we've got the LED ring mount or a camera mount, or we hope to have a servo mount in there as well, and they'll be able to download and print those things so that they can be incorporated into projects. The very end of this week will be a focused lesson on design thinking. There is a design thinking process, design thinking cycle that's pretty famous, which we'll be following in this unit, where you begin by empathizing, and then you ideate, then you define, you build a prototype, you test something, and then you repeat it again. So students understanding that this is the process that you go through as you design a product is really important. So the next week, now we're into week 5, 2 weeks left. Now we'll do a design challenge practice activity. A teacher has some problem. Oh, I need a security system, something. Okay, we'll let kids work on that. We've got all of the tools available for you. It could be done as a recipe, but we'd like to let the kids or the students practice on that. They'll present, share it, review it as a group, evaluate and modify, go through all those steps in the design thinking. The next day, that's when, middle of week 5, we'll have a proposal from the National Design Challenge, our live Google Hangout, where we'll say, here's our design challenge, and there's 2 days to get it done. Are you ready? Go. And this will be um, modeled kind of after a hackathon, something that they have the tools to work on, but yet there's a lot of opportunity for variation. So day 4 and day 5 that week will be a work day and submit the project. There'll be some sort of a video submission that goes along with it, so that they're explaining what they're producing. And then we're on to our last week, week 6, make it local. So the first day we'll break our group into several teams who will work on one of the improve our Upward Bound office projects. If I have 15 students, I'll break them into teams of 3 or 4, depending on how many projects I've chosen. One could be a scrolling LED sign powered by a Pi. It means I'm going to take one of the extra Pis that I buy and set it up with a LED sign. Maybe a monitoring the 3D printer project, a weather station on the Upward Bound building, a Pi-powered attendance mechanism. These are some projects that will have a tutorial built out, but again, this is some of your students working on, let's solve this, let's mount it, let's turn it in. Let's make our office, our Upward Bound program a better place. So I imagine that'll take 2 days to get those things up and submitted. On the third day, this is when I invite local stakeholders, and I call them stakeholders because they are people who are interested in your program. That means if you have a university department chair for the computer science department, if you have somebody from EPSCoR in your university, if you have somebody in your community who you just know is really excited about Raspberry Pis, about the students' opportunities here, invite them. There's one person in particular that you're going to be trying to find, and it's somebody who has a community issue that you think might be able to ask the students for help on that kind of issue. So when the stakeholders visit, I'll let the kids show them about what they put together. They can ask for, the stakeholder can ask for help, and the students can practice interviewing and empathizing and understanding what things are. We'll have a national live results shared from the competition from the previous week. A celebratory atmosphere. Let's get food in there. Let's make it fun. And then the next day, we'll announce that we've got a field trip. And that local field trip will be to the area with some possible project opportunities. We'll talk about it, have a needs assessment so the kids and the community member helps us map that project out. And then we'll come back, and our very last day will be, let's take it and make it local to where you guys go to school, to where you guys live as a community, and we'll do a little bit on proposing, writing a proposal for the projects that you do over the course of the school year. And those projects, we'll have some examples out there for the students to follow along with, but they come in a grant proposal that gets submitted to UB directors. And my hope would be that if somebody says, hey, I want to put a monitoring station on this kind of beehive out here, then that's going to cost $120 for the equipment and the power source and everything, and they can submit it in some sort of a fashion, and my director can approve that, and then the next year we kind of have our project up and going. So that's a basic overview of that stuff you just saw, and I'd love to talk more about it. So